Hey everybody, welcome back to the next part of our chess engine series. This might be the last part that I record. I'm going to leave this video with some suggested continuations of things that you could try to just make the AI better, make it faster. There's tons of stuff that could be done, and so I think after this video, you'll have an idea of how you might continue with some of those things. So I wanted to solve one final bug that someone had made me aware of, which is this really weird bug dealing with en-passant captures. So say we had this position and it's black's turn to move. Obviously, um, if they move this piece, putting the king in check, we can't capture that piece because then the queen would be seeing the king. So our engine sees that. It sees that and this is, I should preface this is only for those who are using the advanced moves. If you're doing the basic move implementation where you just generate all the moves and then generate your opponent's moves and then see if there's any checks, it will see that this move is not possible. And for the advanced moves, this one should work as well. But the en-passant bug is just for the advanced moves algorithm. So what happens if the opponent decides to play this move here? Now, we should not be able to en-passant capture here, which is a weird thing that happens because it removes both pieces from here, and now we're in check, and our king can be taken. So this should not be a legal move. So our engine needs to recognize that. We can push the pawn forward, that's fine, but we should not be able to capture it. Now, if you recall the way that we, in the advanced implementation, the way that we do checks and move generation is we look at any piece that's pinned to see if it's movable. And so this pawn piece isn't pinned per se, because there's another black pawn in the way. And this is true for, like, if I had another piece. It's not just like let's just say, for example, move a couple pieces out into here. All right, so now this situation changes a little bit. If I have my knight here, now this en-passant move should be possible because the knight is there. So we need to consider this weird situation where our king is on the same rank as where the en-passant pawn is initially, where this pawn is. So for the white king, it'll be on row equal to 3, and for the black king, it'll be row equal to 4. As far as the index goes, and then we also need to look to see if there's any other pieces besides these two in the way of the piece that's attacking. The piece that is attacked could either be a rook or a queen. Both would do this job, so we need to look for that, and we need to check to see if there's any piece in between there. So there's like a little bit of logic that has to go into this move. So I'm going to get started, and then as I go through this, if you want to kind of pause the video and try and like code it yourself and figure out, I'll show you my way of doing it. I don't know if there's a better way of doing it, but I think this is a decent way of doing it. So we'll get into that. Now, I'm going to be doing it in the engine class in the get pawn moves. So I thought about trying to like remove the en-passant moves that follow this, but I think just not adding them in the first place is a better way of doing this, because we already know where they're getting added. They're getting added in this section here where we capture to the left or capture to the right, and specifically in this branch of the if statement here where we set en-passant to true. So there's these two cases that we basically need to look at in a little bit more detail. This one here and this one here. And the logic should be pretty similar. So my thought is, let's check all the pieces or all the squares to the left of that en-passant, and let's see, first of all, if there's a threat. And if there's a threat, let's see also if it's being blocked. So we basically have these two variables, like whether there's an attacking piece and whether there's a blocking piece, and we'll kind of go into that. It's also important that we grab the king location, and that matters. So the first thing I'm going to do is I'm going to add a variable for the king location up here. I could do it down there, but we've already do this check for if it's whites to move or blacks to move. And if it's whites to move, then let's get the king row and column. So I'm just going to create two variables, king row, king column, and set it equal to the white king's location. This will be true if it's white to move. And then if it's black to move, we'll set these same variables, king row and king column, equal to our black king location. And remember, this king location was just a tuple that, I don't know why my compiler's not. Okay, there it goes. Just took a second. This was a tuple that we just keep track of, and every time we move the king, we keep track of its location. Okay, so we have that to start. Now let's go down into the if statement in question here. So we'll start with the capturing to the left first to begin with. So we've already established that en-passant is possible for here, but before we add this move in here, we're going to have to determine whether or not there's an attacking piece attacking our king, and whether or not there's a blocking piece in front of that. And so the way I'm going to do this is with two, like I said, I'm going to have two Boolean variables. So I'm going to call one attacking piece, or is attacking piece, and the other is going to be blocking piece, or is blocking piece. And they're both going to start to be false. So these variables, if they get set to true, then I know that there's an attacking piece. And if blocking piece gets set to false, or gets it set to true, then I know there's a blocking piece in the way, an allied piece in the way, or actually an enemy piece. Either situation, as long as it's not a enemy like rook per se. Obviously, that will not count. That would count as an attacking piece. So one thing we need to know is we need to know where the king is, because it's important that we check to make sure if the king is on this row where our piece started. Remember that for our en-passant move, we're moving forward by our move amount of 1, but our starting location is the row in question, because that's where our king is going to be. That's where both pawns are going to be in row R, and we're removing both of them. So I'm going to first just check to make sure, okay, let's see where my row is. And then I'm going to break this into two cases where checking to see if the pawns are to the left or to the right of the king. So the example I showed on the board at the beginning of this video was the king was to the right of the en passant pawns, but it's possible as well that it could be to the left. And this is just going to decide which squares we actually need to check within this row to see if there are other pieces. So I'm going to check to see if the king column is less than C. So this is that the king is left of the pawn. So the king column is less than the column of the pawn. So first of all, I need to check to see whether or not the attacking piece is inside or basically in between the king and the pawn. Or if it's on the other side, then whether or not there's other pieces in the way, some other piece. So I'm gonna break this into two parts: the inside range and the outside range. Now the inside range is going to be between the king and the pawn, and the outside range, as I'm going to define it, will be between the pawn and the border. So if there's a piece in the inside range that can attack the king, then these en passant moves shouldn't be possible because the king is in check. So like we shouldn't really actually have to worry about that, but we want to look for a blocking piece in the inside. So we want to see if there's some other piece that would block if both those pawns are eliminated. And then for the outside range, well, we want to see if there is an outside piece attacking, and if there's a piece blocking outside. So the king is to the left of the pawn. So I'm going to define two ranges. So I'm going to use my range function a little bit differently here. So as we've classically used it so far, I don't classically, typically, range is typically used with for loops, for I in range, but range really just returns a list of values. So in this case, our range of values we're going to start for this inside is the column of the king +1 up to the column -1. So basically, 1 to the left of our pawn. That's our last one. Now that I actually think about it, oh yeah, because we're capturing to the left. So because we're capturing to the left, that's why we want to do C-1 and not C here, because we know that the enemy's pawn is going to be in the column -1 square. So we want to go up to the enemy pawn in this case, C-1. We don't want to include that. So we're going to go from column +1 to actually C-2, but the range function is inclusive on the first value and exclusive on the last value. So just to maybe illustrate this, let's say our king is here. The column +1. So the king would be like maybe, let's say, in this column equal to 2 square right here. And our en-passant capture is happening over here. So to the right of it somewhere. Since this is a left capture in this direction here, where I'm not going to move the king out there. It takes too long. But let's just say that my king is here and I have like a rook here. The en-passant capture is this one right here. So I need to look to see if there's a blocking piece in any of these squares between the king and my doubled pawns in order to see if this move is legal. Okay. So when I say king column +1, that's the square to the right of the king. And then C-1 is the square of the enemy pawn. So I'm not going to include that in my range function. All right. Now the outside range is going to be in the opposite side of the second pawn. So it'll start at column +1 and it'll go until the end of the board, which I'm going to use 8 here. Now I could use like board.length here, but I know my chessboard's always going to have 8 squares, so that has some meaning to it. But if you were, making a larger chessboard, then maybe you would want to make a variable for the board boundaries, or use like length of board or something like that. What next? So what about if the king is right of the pawn? So our else case here. Then our inside range, we're going to set to be the starting. Here, we need to use the backwards range function, so we need to subtract by 1 each time. So we're going to start with a value that's 1 to the left of the king, which is -1. We are going to go until we hit the pawn itself, which is at space C. And we're going to go by -1. So this will take us up to our pawn, which is on the right, which is to the right of the enemy's pawn. And then our outside range in this case is going to be starting at the enemy's pawn. The enemy's pawn is at C-1. So it's going to be C-2 to the left of our enemy's pawn, and then up to 0. So we're going to go -1. Remember, we don't include the stop. And then -1 again for our range. So we're going to essentially go in the negative direction here. So these both have this -1 as the third parameter because we're counting down. These don't have a third parameter, but by default it's 1. So now we sort of have the variable that we want to use for our for loop. And now we can just check inside the squares in here to see, for the inside range, we're going to be checking for a blocking piece. And then for the outside range, we're going to be checking for an attacking piece. So for I and inside range, notice how like I'm just here, instead of having 2 if cases and 2 for loops, I'm just saving the range function and then plugging it in to my for loop here. If that square that I'm looking at is not empty, so the square I'm looking at is going to be in the row R and then I. If that is not an empty square, that means that there is something blocking it. So some other piece beside, well, it even could be a pawn, but some other piece besides the en-passant pawns blocks. And so in that case, there is a blocking piece. So we can set this blocking piece equal to true. And so now at the end of this method, we can say if there's a blocking piece, then we can append this move, no problem. If there's an attacking piece and there's no blocking piece, then we have to not consider this move. All right, so that's all we're going to check there. Now that's for the inside piece. We don't have to worry about an attacking piece because that should have already been calculated with our checks. We should have already seen this if our king is directly under attack. So shouldn't have to worry about that. But we do have to look at the outside range for both blocking and attacking pieces. So we're again going to check, and since I'm going to be using this square a couple times, I'm going to save it in a variable here. So R and I is just going to be the piece there of the square. And we're just going to first off check to see if there's an enemy color. And here's where, if you guys want to try and finish this algorithm out yourself, feel free to pause the video and do so. I'm going to go through my solution here. I'm first going to check to see if the piece is an enemy piece, and it's a rook or a queen, because those are the two pieces that can attack it. So I'm going to check to see if there's an attacking piece. So if the square that we're looking at has an enemy color in it, and it's either a rook, so this will be square 1, is a rook, or a queen, then this means there's an attacking piece. There's a threat. So I cannot use my en passant unless there is a blocking piece. So some piece is attacking. Now, if it's some other piece, so if it's not blank, that means it's not an enemy color that is a rook or a queen, then that means there's a blocking piece in the way. So this will save my piece in that case. Oh, I have 2 parentheses here, my fault. And so I'm just going to use these booleans here. And the logic is, if this is false, that means I didn't find a blocking piece, and this is true, then that means my en passant move is not legal. All right, so I've now have all the logic done, and I can simply say, if there's no attacking piece, or there is a blocking piece, then let's append this move. So that's where I want to append this move to. Only in that situation. All right, so that's the entirety of the logic for this. Just to go through it again, we started by getting the king's location. We created 2 flags, 2 Boolean flags to keep track of the attacking and blocking piece. We found a range of squares that we wanted to look at, depending on whether the capture was happening to the left or to the right of the king. We checked those squares for blocking and attacking pieces, and then appended the move only in the case where there was no blocking piece and there was an attacking piece. So this logic is going to basically be the same for down here as well. I didn't think too hard about how to combine these into one. I'm not sure if it's actually easy to do or not. So maybe you could put it in a method that's like check for en passant, and you could I don't know. It's a little bit weird because the capture is happening, so it changes like the range functions mostly. But I'm just going to copy and paste that for now. So in this case, now we're looking if the capture was happening to the right. So our range functions have to change a little bit. Instead of the inside range now going from column +1 to C -1, now it's going to go to C instead, because our enemy's pawn is there. So we're just going to change this range function to C. Our enemy's pawn is at C +1, so we want to go up to our pawn. And then our outside range function is going to go from C +2 now. So that's really like the only thing that changes. And then same thing with the inside and outside range on the left. Now our opponent's pawn is to the left, so we only want to go up to C +1 instead of C as we were previously doing. And then we want to start at C -1, which is one space to the left of our pawn, instead of starting at C -2. I think everything else should be the same in terms of checking. So we're still looking at enemy color, all that good stuff. Yeah, I don't think anything else changes. So you could probably put this into a function and then call that function based on this value here. But I'm not going to do that. All right, this should take care of the en-passant bug. So let's go back into our program. Let's run it again, and we'll get that situation again. It takes a little time to set up because it's just like it's a weird bug. You have to move your king out a lot. So I'm going to move my king out here. I'm also I'll check it with a rook as well. So we'll put a piece blocking. We'll do that. I shouldn't have done that one. Let me undo that move. Okay. Let me just get our en-passant in ready to go. All right, so here, this should still be fine. This en-passant capture should still be fine, which it allows us to do because there's a knight here blocking the way. But let's say they move the knight. We're not in check. We're still fine because we have white here, but we can't move this pawn. Let's check to see if, okay, so it's white's move. So let's make a move for white. And then here, and now you can see this en-passant capture is not possible. It's letting me move the piece forward, but it's not letting me capture because then my king would be in check. Same thing on this side. It's letting me move forward. Now, if I have, let's see, let me move, oops, that's a check. So let's move this back here. Now, if I put, let's say, this knight in the way and have this, now this en-passant capture should be possible because this piece is blocking the check from the queen. So that's valid. And if I move it to the other side, let's say, then that's possible because it's blocking on that side. So it looks like it works with allied pieces. Let's check to see, does it work with other enemy pieces as well? There we go. We're able to capture it. I also put two pieces in the way. So there we go. It looks like it's functioning well. We could test the black king as well. I tested it more thoroughly on my own, so I think that it works as long as I didn't make any typos or anything like that. But yeah, that was an interesting bug. Very, 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 very interesting. I hadn't considered that at all. And I saw someone post it in the comments about it. So thank you for that. I do try and read all the comments. I can't always respond to all of them, but yeah, that was a really interesting bug. So the logic of it was kind of fun to work out and to figure out where to put it in. Definitely difficult. So if you were able to implement this on your own, good job. Good job. And you might have done it a little bit differently than mine. But I think it's relatively efficient. I think I'm only looking at the squares we need to. We could probably add in a break. If you find like a blocking piece. So you could probably check before you like look at the outside pieces to, if you like have a blocking piece, then it's valid. So you could probably save it checking a couple squares to to check efficiency a little bit better. But all right, so that was thing number one that I wanted to do in this video. Thing number two, I wanted to finally get into looking at some like board positions for our AI. So thus far, I think we only look at material still. I don't think I've implemented anything else at this point in time. Let me just validate that. So we look at our piece scores and we score the board based on our finding best move. Let's see, uses this algorithm here and scores the board. And our scoreboard is simply looking at the piece scores. So there's a couple different ways you can implement positional type play. So like one thing we could do is we could like look at the list of moves that we're currently looking at or that we currently have available to us, and we could count like how many attacking moves we have, because like generally the more attacking moves you have, the better your position. You have more threats you can make. So we can just try to create threats in our AI by saying like the more attacks you can make from a position, the better off you are, or the more captures you can make, the better off you are. Not every capture is a good capture, but if you're attacking the enemy pieces, that's better, generally speaking, than not attacking the enemy pieces. We could also have our engine. One thing our engine is not doing is anytime we run into our own piece, we're not counting that as a move. But that's really a defending move. So it might be good to add in like a way of counting how many defending moves we have while we're calculating our moves. So that would be another thing. I'm going to start with something pretty simple. Those other things, I think I'll let you try to add in on your own. I'll give you an idea on how maybe to start those. Maybe we'll do like attacking moves or something like that. But I think reworking the engine a little bit would be needed in order to implement some of those things. So I'm going to simply look at the position of pieces in our board. So up here, I'm going to define a few more arrays. This is like kind of maybe a common, I don't know if it's necessarily a common way of doing this, but like this is definitely one way to play positional chess. So I'm going to start with a simple example of the knight piece. So if you're familiar at all with knights, you generally want to avoid keeping your knights on the rim of the board. And what I mean by that is if we start, oops, I can't run it right now. I have an error. If I put my knight here, I've really limited the scope of this piece. So let me just compare that with moving the knight here. This knight only has 3 options to move, the 2 squares plus the square back, whereas my opponent's knight here can move to 5 different squares. So I've created more options for this piece versus one of my versus my white knight here, which is along the edge of the board. So typically speaking, knights are better to be placed in the center of the board where they can reach and attack and threaten more squares. So what we can do is we can create like a 2-dimensional map of where we want our knights to be positioned. So I'll show you what this looks like for knight. And I don't know, like you can play around with these numbers, these weights. I'm just going to use a scale from like 1 to 4. And so essentially what I'm going to do is I'm going to create a row of my array with 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. And this is going to represent like the top row, so the border. And then my bottom row is also going to be all ones, because I don't want my knight to be on the edge of the board. Now, as it moves toward the center, I'm going to increase the value of this array. So this is like my second row. So this is still the edge of the board. But now, as it reaches the second row, I'm gonna say, okay, well that position is like a 2, because that is like a little bit better. All right, and then as I move inward, so the next row, as I move toward the middle, those are going to get evaluated to 3. And then my second row and column are still going to be 2. I'm just creating a 2-dimensional array of these values. And then finally, as I get to the center, I'm going to score them as 4s. So my 4th and 5th row are going to be the same, my 2 center rows. They're going to score the same for my knights. My 3rd and 6th row are going to be the same. My 2nd and 7th. Oops. And then my 1st and my last are also going to be the same. So essentially what I've done is I've created a score or like an evaluation. So what I can do is I can look at when I find a knight piece, I can say, where is that knight located? Where is its row and column? And I can just look up the value. So if the knight is on this square, it's going to be evaluated with a value of 3. That's better than a knight being positioned on the outside of the board where it has a value of 1. So for my first knight move, I'm going to consider these 2 positions, and my AI will consider this as a better move because it can attack more squares. So this will help our knights to move or jump toward the center of the board, okay, which is where we generally want them to be. So now what I need to do is I need to go I need to go down to my my pieces, and then if it's a certain piece, I need to look up its value in this table. So I'm going to create a dictionary for that called piece position scores. And it's similar to what we did here, this dictionary up here, but I'm going to map each of my pieces to the appropriate 2-dimensional array. So for my knights, I'm going to map them to this knight scores array. So when I look at the value of the piece and see that it is a knight, then I'm going to look up its row and column in this table and evaluate this. Now, I'm going to have to scale these points because the value of a knight is only 3. So I'm going to maybe multiply this by like 1/10. But you could play with these numbers. Like I could have made them all like 0.1, 0.2, 0.3, 0.4, or some value of that. Essentially, multiplying them by weight factors is just going to determine how much of an impact they make on the AI's thinking, how much they make on the position or on the score of the position. All right, so I'm just going to start with this knight one here. And let's see now how to implement this in. So we're going to implement this in our score method. We've already gone through the row and the columns to evaluate this here and add the pieces in. If it's white, we add a certain score, and if it's black, we add a score. This is simply for material. Now, the position part of this is we're gonna have to add that in. So what I'm gonna do is I need the row and the column of the position, and because I used a for each loop here to grab these, I don't have the numeric value of the row and the column. So I'm gonna modify this for loop a little bit. I'm gonna use my range function and my length function. And now instead of just using a for each loop where it just iterates through it, it's now going to, the range function is going to give me a value between 0 and 7. And I'm going to go evaluate all of those squares. I'm going to do the same thing for column. So I'm going to say for column in range length of game state board. And then here I'm going to put row in my brackets. So if you've studied 2-dimensional arrays before, you should have seen this notation. It looks a little bit different in Python than it does in some other languages. But it's just like a 1-dimensional array using the range function and the length function. This length of game state of board is 8. So this is the same as putting like an 8 here. All right, so then we do have to modify this a little bit. So since I already have this square variable, I'm just going to go ahead and define it square as being game state dot board row column. So this is now the piece. This is now essentially is the piece. And so I can look at the color of it. and so on and so forth. All right, now I'm going to put in a check here to before checking whether it's white or black, because now it matters whether it's a piece or not. These both check to see if it um, was a piece inherently, because it checked to make sure that it wasn't a dash. But now we do care about the second part of this. So I'm going to put this if statement in first, just to um, make sure that we don't look at a blank square twice, essentially. So I'm going to make sure that it's not a blank first. And I'm going to go ahead and tab these in. And if it's not a blank, now we'll score it positionally based on what type of piece it is. Now, currently right now, the only piece we have is like a knight. So we will have to make sure that it is a knight right now, but after that we don't really need to check for that. So yeah, we'll kind of simplify this a little bit in a little bit later. But right now, we're just going to check to see if the piece type is a knight, because that's the only position table that we have currently. Otherwise, we'll get an error when we try and check this. All right, so if it is a knight, then we will look up its piece position score. So I'll have its piece position score equal to this dictionary scores, but I'm going to look up knight. So what this does is this goes into here. Let me minimize some of these methods so we're not scrolling through all these again. Okay, so it looks up n in the table here, and it returns this array. And so what we need to do is we need to find the row and the column value in this table and get this number, and then use that number to weight our AI. Okay, so that's this is the array. And then we're going to put in, okay, so this is the knight, and then we're going to look up its row and its column. So this is going to return a number here. And we get this piece position score. All right, now we can continue on. So now we'll look if it's a white or a black piece. And our score will be the material of the piece plus the position score that we calculated in this if statement. And for right now, just so it will compile and run, let's set this to 0 initially, and then for knight is going to be the only case where this matters. So I'm going to add the piece position score, and here I'm going to do, so I'm doing minus equals. I'm going to minus the sum of the score of the material of the piece and the piece position score. All right, so I'm going to calculate it based on whether it's a knight here. And so what we should see now is our AI has the tendency to move. I weighted this very heavily. Notice I didn't multiply this by anything. So if a knight is moving to that center square, it's weighted as 3. So now if I'm going to set my AIs to false here, and I bet you it plays like a 4 knights game. It should. So if we run it now and let our AI think a little bit, it's going to move all the knights. Maybe not. Maybe it's worried about, well, oh, it couldn't move this knight here because either one would get taken. All right, it's doing some interesting movements. I guess it's not quite weighted as much as I thought it was going to be. All right, let's go ahead and stop this. So kind of interesting. It doesn't want the knights to get taken, obviously, because that would be a loss of material. But we see it a little. Oh, wrong move. Wrong. We see it a little bit affect it for the knights, which is what we want. And I'm gonna just add in a little thing for my debug purposes. So I have it print out the evaluation of the move. I'm gonna add something here to my find best move, where after it finds a move, I'm gonna go ahead and print not in find best move, in my alpha beta pruning. When it finds a score that's larger than max score, I'm going to print out the move and the score just to show like it's thinking it finds these best moves as it goes. So let's see that should change that a little bit. So it's looking at a couple of these, and you can kind of see how it's evaluating positions. Some very interesting moves. I think there might be some other bugs we have to look at. It's my engine. I'm looking at depth 4. Okay. Anyway, let me finish up this thought here before we kind of go back into that. Okay. So this positional score is really relying on this table of values that we defined at the top. And so if I modify this, let's just show for argument's sake that I make this 10 points. This square here to move a knight to either of these two squares is 10 points. What you're going to see is that the AI prioritizes that, and it's going to move its knights out to those squares. All right, so we're telling it essentially where do you want to put your pieces? Okay. So it's kind of interesting. We're essentially telling it these are good positions to play with. Now, I'm not sure that my position graph or like my 2D array for positions is the best. I think this is a good way of playing chess, but like I'm not a grandmaster. There's maybe different theories behind this, and I'm not sure how much to weight this either. So what I decided on doing was I only wanted to weight the piece play by like point 0.1. So I wanted it to play material more than it played like position. So I'm going to multiply this like amount by a smaller amount. And that means it's still going to consider those, but it's not going to consider it as much. It's not going to be worth an entire pawn to get it to that square. It's going to be worth a tenth of a pawn. All right, so you have to play around with these numbers yourselves to try and make your AI smarter. So if you're like thinking like my knight's behavior is not acting up correctly, like it's not moving to the squares that I want it to move, you can change the weight of these. Maybe make it negative points to go to the rim. I don't know. I don't know if that's a good idea or not, but like that's what you want to think about. All right, now I want to give you guys a chance to do this on your own. So like if you want to pause the video here, I would like you to try to create scoring arrays for all the pieces. So we still have the king piece, the queen, the rook, the bishop, and then the pawn. So we need more of these. And with the pawns, I actually created 2 because white pawns are trying to get to one square and black pawns are trying to get the other side of the board. So like you kind of need to differentiate those. So if you want to pause the video here and then just try to implement some, and then I'm gonna also pause my recording here and go ahead and copy and paste my values in. I don't feel like retyping them all. And I'll show you what I came up with and you can compare it with yours. All right, so I added mine in here. For the bishop, I thought, where do we want the bishop pieces? I think we probably want to put them on diagonals. So let me pull up. So the idea behind, I think, a bishop is like you want to try to get it on this major diagonal where it can have like a larger impact. So for the dark squared bishop, it wants to be ideally like on this diagonal here. And then for the light squared bishop, it wants to be on this diagonal here. And if it can't be on that diagonal, then one of the other two diagonals next to it, because the scope of that piece, it can hit more squares if it's somewhere on that if it's somewhere on this diagonal, it can have a lot of influence on the board. So again, I'm not sure that necessarily mine's the best way of doing this, and you can play around with it. But what I decided was I would make 4 be anywhere along the either diagonal, and then 3 would be 1 square out from that. So you can kind of see this grid here. And then 2 would be 1 square away from that. And then 1 would just be these squares along this edge here. It still has impact on the game in different situations, so I don't want to weight this position too much. But I think that this will help to move the bishop out a little bit. Like generally, even the first move of the bishop, we want to move it at least like 2 squares. So, it depends, because sometimes actually like, and yeah, I don't know if this is good or not, because like sometimes we want to move our bishop. Let me see if they move their knight here. Sometimes we want to move the bishop to this square here, like if they put their knight here, because we want to pin it to the queen. So like my AI isn't going to be looking at that. My AI says this is a value of 2, which is not as good as like this square here, which is 4. So like again, I don't know if this is good or not. We just have to kind of think about that a little bit. So play around with different positions again. Queen scores is what I did for the queen. Similar logic. I thought, I did it a little asymmetrical. One's on the outer 2 edges, just not as much impact. We want to try to centralize our queen as much as possible. And I thought from its starting location, these couple squares where it moves out, like here and here for the white queen moving out to here, or let me put a space here. So for the white queen moving from its starting position to here is like generally good, because you're attacking this weakened pawn here and can infiltrate in to attack the rook, or here, just applying pressure depending on like where the enemy king is a little bit. So this I think is not bad. It's going to try to centralize the queen a little bit, put it into open spaces where it can have a large influence. Again, you can play with these. I'm using arbitrarily like 1 to 4, but like you could go up to 10 with these, especially if you're multiplying by a 10th. You just have to play around with it and see what works. See what makes the AI like play a little bit smarter. The other thing to think about is creating batteries, like putting your queen on like the same file as a rook is like generally good because they support each other. But that could also go along with like defending pieces. Like you want your pieces to defend one another. So like looking at defending moves in the engine and like counting those. And the more defending moves you have, like the better. So that could also be accomplished in a different way. Right now we're kind of like just looking at pieces isolated. Rooks, I kind of have it on the 2nd and 7th rank as being good. Like generally, if you can get both your rooks to the opposing player's second rank, you can like start eating some pawns and put a lot of pressure on. Also, like just centralizing it in the back rank is generally good. But again, I keep kind of trying to keep it out off the board and centralize it is the idea here. I broke my white and black pawns into two, and they're the same but just flipped. So I have for white pawns, if they get all the way to the end, that's really good. Like because then they're worth a queen. So like I should actually probably weight this as more because like if you can convert that piece to a queen, like that's really good. So I have it like make it more points as it treads down the board. I also try to centralize them. So like obviously you'll never have a piece back here, so like this row could be 0. But I also wanted to move these central pawns. So I said like if it's here, it's not worth anything extra. Because like the D and the E pawn, you really want to try to get out to the center and control the center of the board. And so like this will try to make it so that the AI like pushes the pawns early. And the idea is let's advance our pawns, let's take territory. And black is essentially the same but opposite. I couldn't think of anything good to do with kings. I think like our king is a really interesting piece. I think one thing you want to try and do is like look at king protection, and maybe the best way of doing that is like seeing if you've castled and making it worth like a lot of points to castle. That might be like an option because then that means your king is generally safe. But yeah, getting the king out of the center of the board is generally a good strategy. Getting it castled. But you could also check for like king protection. Like make sure you have a lot of pieces near your king. So I'm not exactly sure how to do that in an efficient way. So I couldn't put it into a table, so I just didn't. Okay, so once you have all your arrays, again, you can use mine or you can kind of come up with your own. I'm sure that mine are not that good. So I thought about it a little bit, but I think there's definitely better ways of doing it. So feel free to use your own. I just want to show you uh, sort of the logic here. The individual numbers, that's up to you to kind of fine tune to make yours smart. I think this will play like a good game of chess, but I don't think it's great. But I'm gonna go ahead and add in the other ones. So we have knight, we have queen, we have bishop, we have rook, and then we have black pawn and white pawn. And again, I don't have king, so I didn't put that in there. All right. So now what do? We got to make it so it considers all these positions. So the only one we don't have is king. So now instead of changing this to be just a knight here, I'm going to go ahead and change it to be if it's not a king. So if it's not a king, then it's going to have a piece position score. And we're going to look to see if it's a pawn. The only one so we could just like we could replace piece position squares with score or with square one, the type of the piece. The problem is this isn't going to work for pawns because pawns can either be black pawn or white pawn. So we'll have to check to see if the square type is a pawn, then our piece position score will be the square itself because we'll pass in the string BP or WP. Otherwise, we'll look at the type of the piece. Okay, so this is for pawns, and this else is for other pieces. And then we calculate that score there, and we add that either to white or black, depending on whose piece it is. If you have a position, I don't have a position table for my king, so I'm going to ignore that. if you came up with a position table for the king and you want to test it out, then you can get rid of this line of code, and that's fine. So if you have that, you can do this, but you'll see what happens if I do this. I'm going to get an error when my AI goes, and it's because the key error of king. So that's why I had to add that in. Okay. So now let's just see how it plays. And it should already play like a little bit smarter than it was playing before, because it should consider moves that you can see it thinking. So it looked at both knight moves, it looked at c6, and it ends up playing c6, which I think is an opening. I think c5 is better. So we'll just grab the center and see what it does. This is kind of like a Caracon, I think. Interesting. Let's push again. Okay. Should take. We'll see if it takes with the queen or the bishop. Okay. And it's playing relatively slowly for only looking 2 moves in advance. And part of that is just we're using Python lists. They're just not efficient. And I'll talk about that at the end of this video. Wow, we're already going on like an hour right now. I'm not going to test too much. So what I'm printing out here, this is like its thought process, if you will. So these are the order of moves that it's looking at. I'm randomizing the moves each time. So it's looking at bishop c7, and it's scoring it as negative 0.6. It's looking at king f8. It's scoring it as negative 0.5. So it's trying to get as close to, it's trying to get the most positive move. And the most positive move it found was knight f6. And this number here is how many like board states it looked at. So it looked at 82,000 different board states in the 4. We should definitely be able to trim this number down. And we can do this in a couple different ways. Like one is like move priority. 2 is like we can just teach it like to play better. So like right now, we're not really considering how many like threats it's creating. Like so far, I think it's played like an okay game, right? Like I don't think it's done anything that's like the pawn moves early were like a little bit weird. It definitely should have pushed these a little bit more, and maybe we make a more of a discrepancy between pawns on rank 3 and 4 to give it a little bit more weight to get those pawns out. Oh, sorry about that. But it's definitely thinking. So I wanted to pause at this point because I think like I'm not going to do too much more with the AI with you guys. I'm going to show you, or I'm going to like talk about a couple things that we can do. But I think at this point we really need to remake the way our engine's running. So yeah, that's a pretty good move. That puts a thread on here. Our engine is just slow in determining moves, and we're looking at too many possibilities. So there's a couple things that we want to do. So to make your AI better, like one thing we could try and do is instead of using 2-dimensional lists of strings, there's something called bit boards. So if you look this up, there's a nice little like Wikipedia article on bit boards that, and maybe I'll link this in the description of the video. Essentially, it can represent a board with a small data structure, and it would allow us to like evaluate positions more quickly than we're doing right now. Another thing we could kind of do is just use like NumPy arrays. So NumPy is another library, and instead of using 2-dimensional lists, we could use NumPy, and they're going to evaluate a little bit quicker. It just uses faster lookup times in terms of the values, so it's not spending as much time doing the calculations. That's not a bad move. Probably going to beat me because I'm not thinking that hard. And I'm not that good at chess. The other thing is like this engine like doesn't know any openings. Every time we run it, it has to recalculate openings. It has to redo all those calculations. So what we could do is we could create a database or use a database of openings. And we could essentially teach it openings. And we could say, like, if the position here, pick one of these couple moves, because these are the best moves in this position as the current theory goes. And then it doesn't have to think as much. Then it just needs to pick a few different moves, or evaluate just a few different moves instead. There's something called transposition tables, where let's say, like, right now, I think did it make a move? Yeah, it made a move. I didn't even see where I moved the bishop here. So let's say, for example, I move my knight here, and then they move their pawn here, and then I move my pawn up. That's no different than me moving my pawn up first, them moving their pawn up first, and then me moving my knight, right? We transpose into the same position, but the engine's going to evaluate that position twice. So one thing we can do is we can essentially take our evaluation for a position and save it. The way you do this, there's something called Zorbist hashing. So you essentially hash, and if you're familiar with hash functions, you can create a hash function for your board. You save that with the score that it calculated and the depth at which it calculated, and then you can read that in, and this will essentially give you a good starting point for your AI. So it doesn't have to look at as many positions. It'll look at positions that it has already evaluated and had a good chance of being a good move. The other thing we could do is we could have it start with values, or start with board positions that it's already evaluated as being good. So, like, as it prints out these values here, like, and it's like, okay, so it looked at knight a6 and found that it's point a3, which is this move here, knight to here. And then it looked at knight e4. So next turn, if like, I'm going to just take it. Oh no, I can't take it. I'm pinned. Good move. Okay. Like, next turn, it should start with by looking at knight a6, because it already said knight a6 was like a decent move. So we should start the evaluation there rather than like starting at just some random move. So that's like another improvement that you can make. You can save the moves that were good and evaluate those next time. That's one of the things with our engine. The way that we do it is we recalculate the moves every time. And I think this is not a very good way of doing it, actually. Because we run into a lot of weird stuff that can happen. Look, it's looking at castling. I don't know that we necessarily want to, like, regenerate the moves each time. I think this is another thing that's causing our engine to be kind of slow. If you think about a chess position, when you make a move, most of the moves that are still legal are the same. Like, obviously checks change that a lot. All right, but this queen moving here, what did that change from Black's perspective? It didn't change any of the moves that any of these pieces can make. All these pieces can still make the exact same move as they could before. There's the only thing that changed was that the king can now move to this square here where the queen was. So basically what you have to do is you have to look at the starting and ending position of the moves and look at any piece that can move to that square now. And for the ending position, you have to look at which moves it blocked. And that's true for white as well. Like, did it block? Is the queen being here block any moves? Obviously, it took a pawn, and so that pawn can no longer move. So we'd have to remove those moves from the board. But that's the idea. When I move my knight from here to here, I didn't change the fact that this rook still only has 3 moves, or 2 moves, and this rook only has 2 moves. Well, 3 moves if you count castling. So I didn't really change anything. So I don't think that we should get too worked up about like recalculating all the moves every time. And I think that's one reason why the engine that we built is so slow. So this would require you to go. I'm going to go ahead and pause this thrilling game of chess. Uh, this would require you to go into the get valid moves method and sort of redo how it's calculating moves. I think I would suggest actually saving in the state of the board, saving black's possible moves and white's possible moves. This will also help with transpositions, because if I transposition into a position that I've already been in, then I already have the move saved for that. And essentially, if you use like a database, you could save positions and their current moves as well. So you wouldn't have to recalculate those. You could just like read in the moves that you've already calculated, and you'd only have to calculate the moves in positions your chess engine hasn't been in yet. So there's a lot of improvements that we can make to just make our AI be able to evaluate positions faster. And that would enable us to go and increase this value. Right now, we're only looking 2 moves ahead just because we have to consider so much. This would allow us to really crank up the depth that our engine could go at. So that's one thing. That will make this smarter because it's just looking further ahead. We could teach it endgame theory. Like right now, endgame theory, like ours doesn't really do that. And so like we could have it so that, if the material on the board gets to a certain point, then it changes the way that it thinks. And we could have it look so like start evaluating moves with that of pieces that are under fire. So like if a piece is under attack, look at either capturing or moving that piece first, rather than like moving a pawn, right? Look at threats first, so we can have it think about moves that are going to be more impactful first, and that way hopefully we could drive this number down. That's one goal. We want to drive this counter down while still playing good chess. Ours doesn't evaluate really pawn chains. I mean, positionally, I don't think it's really putting any merit into pawn chains. So you could have it so that if it chains pawns together, it scores more points. All right. So just trying to give you some ideas. Again, like I said, I don't think I'm gonna do any of that. I've done some of this in the past. I don't necessarily feel like doing it again. It gets kind of complicated, and I think to show it all, I almost at this point kind of want to scrap the engine and redo it from scratch, um, and maybe use a different data structure, or a different way of storing the engine. I just don't. I don't think we're going to get to that optimization point. And I think if you go back to video 1, I sort of said that from the beginning of this series that was going to be the case. So you can certainly try and like change the way that we're storing the board. Like I think this is really inefficient in and of itself. The fact that we're using strings here, but like I said, that's gonna make us change like everything in our code. So, and I think our move generation is another part where it's not very good. So I think those two things are gonna factor a lot into this. Yeah. The other thing that maybe you want to do is I think keeping like a move log is good, or like a possible moves log, where after you calculate the moves, the valid moves, you don't have to recalculate the moves. Like when we undo a move, we recalculate all the moves, but we've already calculated them, obviously, because we're going back to a previous board state. So that's going to just save a lot of time in and of itself. Is just like storing the possible moves in a list, so that every board knows what white can do and black can do in every situation. I think that will almost theoretically double the speed of your engine, because think about how many times in this algorithm, just for example, in the last one executed 52,000 times. We make a move and then we undo that move. When we undo that move, well, I guess we are still saving the valid moves here. So maybe that's not the case. Definitely for transpositions, it would help. getting to positions we've already been in. Yeah, and then saving those in some external file or database where between runs of the AI, we don't have to recalculate moves, I think would also help. So just some thoughts I have on the AI itself. All right, so the last thing I think I'm going to do for this video series is showing you guys some threading or multi. I think it's called multi-processing. I think is the class we're going to use. Yeah, multi-processing, so that we don't have to wait when our AI is thinking. Like right now, when I run it and play a move and I wait for my AI, if I try and like click on stuff or like move the map, it's unresponsive, and I get like, yeah, I actually can't see it on the stream, but like I get the wheel of death and it like blanks and then finally like it tries to move. So I'm going to show how you can still interact with the board while another more computational heavy process is going. And that's going to be where I wrap things up with this video series, because this video is getting a little bit long. All right, so I'll try and go through this kind of quick. So we're going to actually do this in main. I'm going to use a class called multiprocessing, which is included in, oops, not underscore multiprocessing. We're going to use the process and the queue, which are two functions within multiprocessing. You can also use thread, the thread module. From what I've read, multiprocessing is better when you have calculation dependent threads that you want to do, whereas threads are better for like if you're not sure how long it's going to take, but it's not really computational heavy. And what this is going to allow us to do is it's going to tell our AI, hey, go find a move. But while the AI is finding a move, we're still going to be able to interact with our board. It's still going to look at mouse clicks. It's still going to look at all that stuff. So I'm going to add a couple of flag variables in for this. So the one thing I'm going to do is I'm going to add in a variable called AI thinking. And this is going to be true whenever the AI is currently trying to come up with a move. And it's going to be false whenever the AI is not thinking. I'm going to also have a variable called move finder process, which I'm going to set to none to begin with. And this is where our multi-process library comes into play. Okay, so what we're going to do is we're going to play around with where our AI logic is, which is our AI move finder down here. And we're gonna move a lot of this stuff around from what we have here and make this a little bit better. So now I want to add in a call to my flag. So I only want to run this if statement if the AI is not thinking. So I only want to call this like one time. So if it's the AI's turn and the AI is not thinking, then I want to have it come up with a move. So what I'm going to do is I'm going to set this AI thinking to true. I'm going to go ahead and print just thinking. And then this is where threads get complicated. So when you have threads, they don't have shared data. So I can't have this variable AI move in this kind of process in this thread, and then also have it have a different value and read that value in a different thread. So there's no data sharing between threads, but that's kind of not great because we need to know what move the AI came up with. So the way we do this is there's a couple different ways we can do this. We can do this with like a dictionary, or in this case, a queue, I think makes a lot of sense. A queue follows this first, last in, first out. It's essentially like a line. It's different than a stack. queue, you like put things in, and then the things you put in get taken out. So first in, first out. Yeah. Anyway, that's this multi-processing thread. So we're going to create this queue, and then we can put things into this, and we can remove things from it, and the process will keep track of the data that we put into this. So it's essentially going to be just like a container for values that we want to see that were maybe changed within the thread itself. And now we're going to define this process. So a process is pretty simple. The first thing it has is it has a parameter called target. And the target is the function that we want to call. So in this case, our target is this smart move finder dot find best move. But rather than calling the function like we had before with the parentheses and passing parameters, we're just going to say find best move. We're not going to put parentheses here because we're not calling the function. We're passing this function as a parameter. So we're telling the process when the process starts to call this function. That's the way threading works. And then we also have another parameter called arguments. And so the arguments we're going to pass in are going to be the same as the arguments we had here, which are game state and valid moves. And then we're going to add one additional parameter here, which is this return queue. And so when I pass this value in, I can put things into this queue. And then when we finish this process, we'll be able to read in data from that queue. So this is the return queue is used to pass data between threads. Okay, so that's what we start with. Now, when you want to start a process, you just call that process dot start. And this will call the smart move finder find best move with these parameters. So essentially, it would be the same thing as writing this method here. But what this does is this creates a new thread of computation for this thing to work in. And so the rest of our code can continue on without thinking, without like having to wait for this thing to finish. So I can get rid of this line of code now. All right. And I don't want to do this part yet because I don't know if the AI has made a move yet. So I'm going to check. I'm going to check to see if this process is still alive. So there's an isAlive method for the process, and this just says whether or not it's still thinking. I can't use this flag variable AI thinking because I haven't set it to false anywhere, and I'm not going to be able to set it to false in this process. So I'm essentially seeing if this thread's alive. And when this thread is no longer alive, it's either it's done thinking or it's been killed, then we can print done thinking, which we'll just like put in console. I just want to show you don't need these print statements, but I just want to show you how it's happening. And then the move itself we're going to grab is going to be in the return queue. So we're going to be able to access this return queue, and we're going to call the get function. So it's going to give back whatever we put in the return queue. And then we have the move. And then if the move is none, we'll still do a random move, and then we'll make that move just like we did before, and we will set AI thinking to be false. Okay, now there's a couple, like there are some like weird little bugs that come up with this when we undo a move while the AI is thinking. It confuses it. And we also still won't be able to click because we're limiting our handlers based on whether it's human's turn or not here. So like when I run it now, I think I might need to do something in the AI still, actually. Okay, yeah. I didn't add that in yet. So we still have to do a little bit more. So let's go where we call that first. Then I'll get to these things. Okay, so it's changing the find best move. We've added a third parameter to this return queue. So we have to add that into our smart move finder. Find best move. And we have to add this return queue in here. What does this look like? So, sorry, I'm just finding my notes here. So now what we need to think about is I can't use this global next move. I can't return this anymore. Like this return isn't going to do anything because it's in a different thread. And so like it doesn't quite work. So what we're going to do instead of returning it is we are going to put this into our return queue. So I'm going to say return queue dot put next move. All right, so it's still global. We're still setting it to none, and then whenever it's finished, we're still putting it into the return queue. So that's the difference. I think everything else should be the same. Let me think if I need anything else. I think that's it. Let me see here. Yeah, I think that's it. So the process starts. We pass it a return queue. Whenever this method finishes, it puts something in this return queue. And what's going to happen is after we start this process, the process is still alive. So it's actually going to skip over this and it's going to continue with drawing the game state and continuing moving on. So we can now enable our mouse clicks to actually do something. So here, what I'll do is I will still allow it to click on the board. I just won't make a move. So here, I'll change this. This was after the second click, we made a move and we printed that move. But since it's not the player's turn necessarily, let's put the check for if it's a human turn here. And then we'll only make the move if it's the human turn. And then I can get rid of the human turn check here. All right, so I'm just changing where I do that. I'm allowing the player to click on the board, but I'm not allowing them to make a move. And then we'll still be able to press keys, and we'll have to do something about undo moves because it gets kind of weird. But let's go ahead and stop and rerun this. Oh, I'm so sorry. I think for the last few minutes, oh my gosh, I had a board up over the code. Shoot. I don't know how much you guys didn't see. I don't really feel like re-recording this though. All right. I think it was just this smart move finder. So, and hopefully it was far enough let me see if I overlay this again. Okay, you might have been able to see like some of it. So let me go through this again. So the best move part, I just added this line here and took out the return. So we put it into our queue and then added this parameter here. And that was the only thing that changed. Okay, and then in our main, I switched the if not game over and human turn here, and I put the and human turn here. So we're gonna be able to look at clicks here, but not actually make a move here. I apologize for that. Okay, so now when my AI is thinking, I'll actually can still see how now I can click on it and I can actually see the valid moves for black. I can't actually see the valid moves for white. And the reason I can't see the valid moves for white is because my engine doesn't think that white has any valid moves because it's black's turn. This is another reason why it would be good to generate both black and white's moves in a given position, because then you could actually look at them and you could actually see them. So again, I make a move and I can now, this is my thing is thinking in the background. You can see it's thinking and it's coming up with moves. And then once it comes up with a move, it makes that move and it says it's done thinking. And then it returns and now I get to move. All right, so that's threading. One bug you'll see with this is when you make a move, if you try to undo it while it's thinking, I believe it will crash. Okay, no, it didn't. It doesn't crash. Does it automatically? Okay, it saves that as like its previous move. So like if I make a move, let's say for example I do this because it's going to think of this move to go next. If I undo that and then let's say I do something else like this, it's going to automatically do that last move without thinking, and it might not necessarily be a good move. Okay, so that's a bug that we have to deal with in our undo move. And so we'll do one last thing in this video, which is to deal with that. So I have to look at this undo move part, and what I'm going to do in here is I'm going to see if when I undo a move, I'm going to see if the AI is thinking currently. Because if the AI is currently thinking, what I want to do is I want to kill the thread. So I can call this terminate method. It's going to just kill the thread. Now, any processes that are already running are still going to be running. So any recursion that is already happening is still going to happen. And there's not really a good way of killing all those threads that I know of. But I can set the thinking to false. And that way, at least, it won't automatically make a move. Oh, and then there's one, we need one more variable, which I'm going to add up here to indicate that a move was undone. My main class is so bloated right now. All right, so whenever we undo a move, I'm going to set another flag here. Move undone equals true. Move undone equals true. Oh, and then this is for resetting the board. So I'm going to do the exact same thing for resetting the board here. If the AI was thinking, let's reset it. And then here, I'm only going to make the AI think if the move was not undone. I don't want it to like start thinking again if we just undid a move and the AI was thinking before. I don't want it to continue to think. I don't want it to start another process until it's its turn. And I've made sure that we've undone that move. So that little check there will prevent it from like redoing a move right away. And then we just need to make sure that after the move is made, we set move undone equal to false. And just kind of like our move made method. So once it actually does undo the move, then we set that to false. And so now it shouldn't automatically just redo whatever move it came up with. We should actually see it pause and think again about that move. So if I'm just going to undo it right now, and I'm going to remake that same move, and it restarts its thinking. And again, it comes up with C6, which is really a weird move, and I think positionally not great. But okay. I mean, it's fine. I think it's the Caricon opening, so I think it's fine. All right, but we actually can, now I can actually undo. It starts to think again. I can undo my move, so we're not getting stuck in that thread. You can move the window around. You can do move highlighting while it's thinking, and that should be a nice little quality of life thing. Not sure why it was like doing this p.init again. It's kind of interesting. But Yeah. So I think that's where I'm gonna wrap up the entirety of the series. A couple things to think about, and maybe I'll post some of these in the description. But this video is already like an hour and a half, so I think it's a good way to wrap things up. Uh, I just have like a list of things I thought of to continue to add. So you could try and add like a menu in here. One of the problems with like our main loop right now, I feel like it's getting a little bit bloated, and putting these into subroutines, I think to organize our code would be probably good, or maybe even creating like a state manager class would be good, or a module. Um, but yeah, putting in a menu where you could select options for AIs, that could be something you could do. Having a option for flipping a board so that you could see it from black, or you can play as black as well, would be good. Uh, Doing the mouse click and drag instead of the double click. There's a couple rules we didn't implement yet. So we didn't implement 3-move repeating draw or 50-move draw. Neither of those have been implemented. As far as the structure of the engine itself, maybe using a NumPy array or a different data structure to represent the board, I think would be good. You can take a look at bit boards, hashing the board positions so that if we visit a board that we've already seen, we don't reevaluate the moves, and we could like start with a move priority. Prioritizing castles, pawn chains, pieces under fire. Right now, our smart move finder shuffles the moves whenever we at least the first set of moves. After that, it doesn't shuffle them. But move ordering would be important, and you could do that actually right here in the calculating the moves. Once you get all the moves, what you could do is you could check to see and do like attacking moves first. So or do piece moves first, like move pieces before pawns, move bishops and knights before moving rooks. Like check that, and then it's gonna check those moves before it checks the other ones, and you're probably gonna be able to get this number of moves that it evaluates to go down, and it'll just be a little bit faster. All right, so those are just some different things. I encourage you guys to continue to work on this on your own. I think for now I'm going to be done with this video series. I enjoyed doing it, but I'm a little bit tired of it. I've been thinking about this program a lot, so I'm going to take a pause from it. I think I'd like to do another video series, and I'm thinking maybe like a side scroller type game, or like a platformer would be kind of fun to do in Pygame. It's not something that I've ever done before, so I could maybe take you through that process as well. But yeah, I hope to maybe continue to just do some basic tutorial coding, and I can do a couple different languages. And yeah, I, if as long as I keep enjoying it, I'll keep producing some content every once in a while. This isn't my main thing. I have another job, so I have to prioritize that and just do this in my free time. But I am enjoying it, and it seems like a lot of you guys are enjoying it as well. So I appreciate all the nice comments that I've gotten. So yeah, I'll wrap things up there. Thanks a lot. I hope you will check in on future series. Take care.